Okay, so we're resuming our workshop and starting a new session on a new third NBS, which is about increasing plant cover, which will bring about a host of benefits, but among those limits reduce soil erosion. And so in this session, we have a 2-hour session. So first, Astrid, Camille, and Ezzedine will report on their findings on this NBS. And then, to put things into perspective, we'll hear a keynote speaker on this topic, who is Olivier Evrard from LSCE. And so we will also have 40 minutes to put things into perspective and shed light into erosion in general, and looking at mitigation measures at the scale of agricultural catchments. Okay, so dear students, the floor is yours for Olivier.
Thank you, Mr. Evrard. Good morning for everybody, and welcome to the third presentation for the NBS for the second day of the workshop. Today we are going to present the increasing plant cover to reduce erosion. Soil erosion is one of the main problems that cause land degradation, and it's the removal of soil from the land surface, which is caused especially by two kinds of erosion agents, which are water and wind. For water erosion, we have the detachment of particles because of rainfall, their transportation and their deposition, and it depends on the intensity of rainfall, the type of the soil and the runoff. For the second type of erosion, we have the wind erosion. We have actually three kinds of wind erosion. The suspension one, which is the detachment of the smaller particles that have a diameter less than 70 micrometer. It's spread on the air. The second kind is the saltation. It's a little bit more in time in terms of size. Diameters are comprised between 70 and 500 micrometers. And the third one, which is the most dangerous, because it's the transportation of bigger particles for a diameter more than 500 micrometer, and it causes damages to vegetation, to land cover, and to the soil. Here we can give some information about the problem of erosion around the world, as it was given by the Global Soil Partnership led by the FAO. It has been estimated that 75 billion tons of soil are eroded each year, and it's the equivalent of $400 billion. Also, we have 3 million hectares of arable land lost each year in the world due to this phenomenon. And the reduced soil erosion can potentially have an impact on up to 3,200 million people around the world. Here are some challenges for the erosion in the future. With the change in climate and in land use, we are expecting a decline of the soil organic carbon by about 99 gigaton in 2050. And as you can see in the first map, the spatial distribution of soil erosion and its intensity on a million hectares per year during 2015. And as it is mentioned, it's well distributed in Asia, in Africa, this sub-Saharan Africa, and in Latin America. For the three other maps, we can see that using the global system for erosion modeling and using three different values of RCP, we are expecting a higher percentage of soil erosion change between 2015 and 2017. Okay, To counteract this phenomenon of erosion, a natural-based solution can be implemented, and as one of the solutions, we propose increasing plant cover. The percentage of the plant cover is actually the percentage of soil which is covered by green vegetation, and it describes all types of ecosystems, natural and modified ones, such as grassland cover, cover crops, and forest cover. Here are some kind of methods to evaluate the land cover and to detect the change in vegetation. We can use satellite images. We have such kind of low resolution and open source of satellites, such as the Landsat, which is like for 30 meters of resolution. We have Sentinel-2. It's also an open source with 10 meters, and it's a good resource for us because it's open source. We have also other high resolution up to 0.2 meters, like about 23 or 50 centimeters, and it's very expensive, like Quick Bird, like Earth Watch, and other kinds of satellites. We have also this from remote sensing, and using geographic information system to restore and to treat that kind of data, especially using vegetation indexes. Here, the famous one is the normalized difference vegetation index and NDVI. It's based on the difference on the reflectance of bands of the red, the visible one, and the near infrared. The near infrared is the band where we have like the most reflectance for vegetation. It has values like range from -1 to 1, and all the values the positive values refer to vegetation. Okay, to develop our presentation, we divided our project in 3 main parts. For the first part, we will talk about the different impacts of our NBS in different targets. The second part, we will talk about our case of study, which is the Grain for Green project, the same example that was written yesterday morning in during the first presentation of afforestation. But here we will define it again, speak about the different circumstances of why, when, and where it has been implemented, how it has been evaluated, and the different impacts or limits of the GGP. For the third part, we will talk about our research question that we will explain later.
So, as said before by Ezzedine, the first part of our presentation concerns the impact of the NBS increasing plant cover to reduce erosion on 6 different targets that are soil quality, food security, biodiversity, pollution, human health, and climate. So now let's start with the impact of plant cover on erosion. In this graph, we can say that different types of plants, that are trees, grass, and shrubs, have a positive impact on limiting erosion. And when we start with the leaves and the trunks. We see that they can intercept the rainfall and then decrease the energy of the incoming droplets. And when the droplets reach the soil with a low velocity, it decreases the risk of erosion, of water erosion. And another fact is that the fact to have the soil covered by plants reduces the risk of runoff, because of course a bare soil is more susceptible to have runoff than a covered soil. And another advantage of vegetation is in the roots. And for grass roots, for example, that are not very deep, they protect the surface ground layer. And for the trees roots that can be very deep, they allow to have good, consistent between the different layers of the ground. And another advantage of plants is that they permit to have a good soil quality, because by decreasing runoff, they give power to infiltration, and the soil with a very big water content is more qualitative than the soil without enough water. And also, there are a very big source of biomass of the soil, because when the leaves of the trunks or sometimes of the plants die, it is a very good source of carbon for the soil. And in what concerns food security, that is a little bit a consequence of the advantages on soil quality. We see in this graph that plant cover allow to increase the ability to have food security, because it increases the yield and also it increases the quality of the food produced. So it increases the yield. Why? Because the fact to have plant cover cause less removal of soil organic matter, it has previously been seen. And when there is more organic matter in the soil, the consequence is that there is more water and cation retention by the plants. And the cation and the water are very important for the plant metabolism. So then when there are more in the soil, they can allow to double or sometimes triple the productivity, and of course it will allow to have more quantity of food. But food security doesn't only concern the quantity, because the food produced should also have a good quality. So that is also an advantage of plant cover, because when they are, for example, used as cover crops, they protect the soil and its nutrients, and it naturally increases the ability of soil to produce. It's not necessary to add, for example, for fertilizer that have a bad impact on the quality of food, and then it will increase food security. And plant cover also have a positive impact on biodiversity, because of course when it decreases erosion and it allows the proliferation of vegetable species, it will be a cause of an increase of biodiversity, because many type of plants will be able to live in the ecosystem. And also it promotes the proliferation of soil biota, because the biota use organic matter for their metabolism, and when there is more organic matter, of course, there will be more soil biota. And there is also a positive impact on aquatic species, because plant cover reduces runoff and the sedimentation of the water will also decrease. So it has a positive impact on water pollution that will protect the aquatic species habitat and then increase biodiversity.
Okay, another impact for increasing plant cover on pollution and human health. For the impact on water pollution, we have two kinds of effects, the on-site one and the off-site ones. For the on-site effects, plant cover can limit soil aggregate breakdown and the detachment. Also, it can reduce runoff, speed, and volume. It has a preventive action because it prevents losses of soil nutrients, organic matter, sediment, and pollutants. For the off-site effects, increasing plant cover can limit the transportation of eroded soil to aquatic ecosystems. It has also a preventing action of water eutrophication. For example, cover crops could reduce nutrient and pesticides runoff by 50% or even more. For the impact on air pollution, by increasing surface roughness, plant cover can reduce wind speed, and it intercepts a proportion of wind transported eroded particles. Then it reduces the transport flux. Also, it contributes year, and it decreased. We have a decrease of respiratory diseases affecting human health.
So now concerning the impacts of increasing land cover on climate. So increasing land cover to reduce erosion can have impacts on local and global climate. So for example, when there are extreme events, coupled with land use pressure, there can be strong wind erosion. But increasing land cover can reduce wind erosion by mechanisms that we described, such as decreasing wind speed or intercepting some of the eroded particles. So it means that land cover will reduce the amount of eroded particles that can be transported by wind. And these eroded particles could lead to local dust emissions, but also dust storms that can travel thousands of kilometers. And they can then deposit on mountain snowpack. So this will change the albedo by decreasing the albedo, and then there will be less radiation that can be sent back to space. So it means that it can lead to a warming of the surface. So Vancouver can have an effect on the emissions. But it can also have impacts on greenhouse gases. So first, increasing Vancouver means that there might be more carbon sequestrated in plain biomass. But Vancouver can also reduce water erosion by decreasing water runoff or improving the soil structure by decreasing the attachment of the soil particles. So there will be less eroded soil and carbon that can be transported by water and into waterways. So some studies, such as the study from Jason in 2001, show that there can be a mineralization of the soil and carbon during transport at a rate of about 20%. And this mineralization means that there will be a release of CO2 into the atmosphere, so greenhouse gas emissions. But this process is not well understood yet, and some other studies argue that there might also be a storage in industrial deposits or aquatic ecosystem. So on the other hand, the eroded soil and carbon can lead to a carbon storage. So it shows that this is still, there are still need for further research on the effects of eroded soil organic matter.
Okay, for our phase of study, we chose to work on the Grain for Green project. This project is a huge one because it was described as the largest ecological restoration project in the world, with a financial investment of about 46 billion euro. For this project, it was launched in 1999, normally for 8 years, but it was extended for another 8 years in 2007. The main objectives of this project were to convert a total of 15 million hectares of agricultural land and about 17 million hectares of barren mountainous wasteland in forests to grasslands or meadows. Also, it has to limit soil erosion and fight against desertification and especially grazing, because it is considered as one of the most impacts of most kinds of soil erosion. Also, it has to protect unsuitable land and land with steep slopes, because in the study area we have about 4 million hectares of land are in slopes that are about 25 degrees or more. And farming in that kind of land will increase erosion for about 4,000 kilograms per year. Another objective for this project is to increase the yield of certain low-yielding cereal crops and to fight against rural poverty. Okay, for the spatial distribution or the area where the project has been implemented, We can see in the first map that when it was launched in 1999, it occupied also only some provinces in the center of China. But 1 year after, during this year, it was limited in a small area because it was managed only with the local government. But 1 year after, and thanks to the contribution of the state government, it was extended to cover 13 provinces, and in 2002 it covers more than 90% of China's area. It covered the 25 of China's 31 provinces.
So after describing clearly the GDP, now we will show how it has been evaluated. So this is one of the way of assessment, the MMF method, Morgan and Camille method. And the goal of this method was to assess the runoff and the erosion dynamic during the project. And this assessment has been done in a part of the area of implementation, that is Zuli River Basin, and between 1999 and 2006. So this method starts with the remotely sent satellite image, and from this image, the land use land cover change was derivated. And after this, the study area has been divided into different hydrological units, and an hydrological unit is defined as a unit with the same hydrological characteristics. And since these units have been clearly defined, the precipitation data are incorporated in the model because precipitation influences the runoff and also the transport of the particles. And once it's done, the model is run, and after this run, we have two outputs that allow to characterize erosion and the transport dynamic in the area, that are annual erosion rate and annual transport capacity. And another way of assessment was the use of remote sensing in order to know how the ecosystem services has been impacted by the project. And for that, some special remote sensing stations have been built in the area of the implementation. And in this study, we can see in the chart the different stations in the map, and we see that there have been more than 100 stations that have been built in order to know how ecosystem services, that is to say carbon sequestration, soil organic matter, and also erosion, are evaluated during the project. And that is the last way of assessment that we present in our project, in our presentation. And it is a combination of statistical tools and on-site measurements in order to compare the effect of different kinds of plant cover on the erosion. Because as the different plant covers have the same characteristics, of course, they won't impact erosion with the same way. So the objective of this tool was to use a statistic in order to know which plant cover impact more or impact less the erosion. So the studied area is a part of lowest plateau of China that is shown again in this card. And the study has been done in 2015. So the steps are described here. So the first one is to calculate an index of biodiversity. And after this, the different characteristics of Houay erosion are calculated in order to calculate later the Houay erosion. And once it's done, they use a statistical tools, analysis of variance, that's called commonly ANOVA, in order to compare the different effects of the plants. And the result of this study will be presented in the next step by Camille.
Okay, so now we are going to see the impacts on the Green for Grain project, for several projects. So the first one is erosion control, because it was the main objective of the Grain for Grain project. So here is the loss plateau region with the method that was described just before by Astrid. So the study compared the intensity of the erosion for different types of land cover. So in the study, sloping farmlands are converted into grassland or woodland or acres. So we can see that with the conversion of sloping farmlands into grassland or woodland, there is a reduction of the intensity of the erosion by at least 90%. But on the other hand, when converting sloping farmland into acre, it leads to an increase in the intensity of the erosion by at least 60%. So it shows that we have very different results on the erosion for different types of land cover.
And now we present the impact of the project on biodiversity. And we have to say before all that there were 3 types of plant cover that has been used during this program. The first one is to plant ecological trees, the second one economical trees, and the last one was grasses. And the Chinese government gives subsidies for different plantations, but the problem was that subsidies for trees were most important than the one for grass. So the consequence is that the farmer preferred to convert the area to grease than to grass, and the consequence was that more than 80% of the area were planted with trees. And that may be why sometimes the program is considered only as an afforestation, but there were also grass planted in the area. And the fact to plant only trees shouldn't be maybe a big issue concerning biodiversity if there were many kinds of trees that were planted, but it wasn't the case. Because in most of area, they use only 1 or 2 or sometimes 3 kinds of trees, and this raised a really issue of biodiversity. And in this map, when we take the example of the leaping region, we see that more than 80% of the trees planted was only 3 kinds of trees, whereas all the other kind was planted in only about 20% of the area. And that is why GGP raised a really big problem on biodiversity.
Okay, so now we are going to see the impacts on the rest of the Green for Grain project on food security. So here is the Lost Plateau region, where there was an increase of about 30% of the Grain for Grain project area between 1999 and 2010. So here we have the evolution of the crop yield, the soil area, and the crop yield per hectare. So you can see that in 1999, when the Grain for Grain project was implemented, just after there was a reduction of the cropland area. So it means that the Grain for Grain project could have led to have negative consequences on food security for this region. But at the same time, there was also an increase in agricultural inputs such as fertilizers, but also the use of agricultural equipment. And there was also construction of terraces or ponton dams for irrigation. And as a result, there was an increase in green per hectare. So in this region, there was also an increase in grain self-sufficiency. And the self-sufficiency index was below 95% in 1998, and it reached 102% in 2015. So it means that the Grain for Grain project could have better food security, but it was compensated by other agricultural inputs and also other complementary measures such as terraces or water dams. impacts on the economy and farm migration. So between 2002 and 2004, there was an increase in grain price in China, but the grain farming project was not found to be responsible for this increase in prices because it targets medium productive and marginal lands. And this project also had some economic advantages for the farmers because they received guaranteed incomes from the government. So these incomes are in line with what they had from the land before converting their equipment. So this guaranteed income removed the financial constraints of the poorest farmers, and they could now take advantages of some opportunities in the city. And at the same time, in China, there was also an economic growth at about 10% per year. So it's also creating many new job opportunities. But there was also some adverse effects because the guaranteed income from the government was supposed to last only for the few years after the rainfall project started. But the government was afraid that the farmers would convert back their land if they was not receiving the payment anymore. So they decided to extend this payment.
Okay, for the last part of our presentation, we talk about the research question. But the first question is, how did we formulate this question? After researching and reading several articles related to the GGP, we found that they talk about the different targets of soil erosion, of pollution, of biodiversity, etc. But we find a lack of information about the choice of plant cover that has been implemented on this project. And most of the studies also compare the different cover types without specifying a species composition. Also, species can be more or less adapted to the environmental conditions on the site where plant cover is implemented. But what if a certain selection of species could have been more beneficial or could have led to a smaller mortality rate? Because during this project we had some studies that mentioned that there was a higher mortality rate on the plantations. That's why we think to work on this question, which is how can we best choose the type of plant cover, the choice of species and species combination in order to optimize the effect of its implementation on erosion reduction, food security, and the other targets. For the criteria needed to plant species selection, we know that if a plant is raised in a good environment with the different requirements for its increasing, we will get a successful plantation. But if it's not the case, it will be it will be more fragile, and we will get disease, and it will lead to the failure of the plantation or its death. That's why we have some factors that that are needed for plant species selection, and that are linked to the species, such as the genetic origin, the treatment, the plant is environment, the biotic factors, and the ecological conditions, type of soil, the water needed, etc.
And before the choice of the good species or species combination for the plantation, it's important to know clearly in which site the project will be implemented. So the first part of the project that we propose is to clearly describe the seat of implementation. And that is to say the climate condition of the site. And for this, a meteorological analysis on rainfall, temperature, wind, air, humidity, etc. etc., must be done. And after that, the topography of the site must also be studied, because the slope, for example, has a very big impact on the development of the plants. And the topographic studies can be done if the country where the project will be implemented has enough means. It can directly be done by remote sensing, and if it's not the case, it can also be done manually by topographic survey. And after that, the soil characteristics must also be studied, and for that, it's clear that all the area cannot be studied, so it's necessary to do a sampling in order to choose the great place for the study. And after that, there will be field measurements and laboratory analysis. And after that, thanks to some statistical tools, the result can be extended to all the area. And the water availability must also be studied, because water is a very important factor of the success of this kind of project. And that is to say that the availability of surface water must be studied, and also the groundwater level must be known. And to know this level, piezometric probles can be used. And after that, it's also necessary to study the initial plant cover before implementing a new plant cover. And for this study, we propose remote sensing in order to have an idea on the percentage of plant cover. And once we know which surface is covered by plants, we can use sampling and statistical tools in order to identify the initial species. And once they are known, as seen this morning, there are some diseases, some species that are vulnerable to some kind of diseases. So the last step is to do, for example, a bibliographic work in order to determine the initial species vulnerability to diseases. And
so now we are going to see the next step of the research project, which is the selection of the type of rainfall that optimizes its effect on the different targets that you saw. So now that we have information on the site with the previous work, we could use this information to elaborate a database of potential species that could be implemented. And to do so, we would have several questions that we would like to address first. So the first one is whether we have to use native species or non-native species, because native species could avoid the introduction of invasive species, for example. But we can wonder if some native species might not be more efficient in terms of erosion control. Another question would be if we use single species or a species combination. So in the rainfall project, we saw that single species cover were often used. The species combinations might be better for biodiversity, also limit the spread of diseases. So these two first questions could be answered by bibliographic work. And then the third question would be to study the species requirements to make sure that they are adapted to the site before implementation. So for example, each species has specific requirements in terms of light, water, or soil property. And we could compare the field data that we obtained previously with the species requirements. So we would select only the species that are adapted to the given site. And the next question would be to address the question of the speed of the species establishment, because this might have an impact on the time needed to obtain results in terms of ecosystem services. So now that we have our database of potential species, we could use it to create species combination. So the goal would be to compare our different species combinations to compare them between them to find which has the best results in terms of ecosystem services. So to do so, we could use a dynamic approach, and one type of model that we could use in the inverse model because it uses information on the ranges they uncover to obtain the results on different ecosystem services. So as a model input, we could use our species combination and the information on each species and the type characteristics that we found previously. So we could run our model for each species combination, and as model output, we would have for each species combination results on erosion control, carbon sequestration, biodiversity, nutrient retention by vegetation, and water purification. So these model outputs would be metric result because it's a quantitative study. For example, erosion can be expressed as gram per meter square. And we would like to compare the different results on each of the services between them, so with the same scale. So to do so, we could define a scoring system, for example, from 0 to 5, and we would convert the result for each ecosystem services into a score. So we would gather the score for each species combination into a matrix score. And then we would have to compare different metrics between them to find out which species combination gives the best results. And then so we have to do this before implementation. So to conclude on our nature-based solution, so increasing land cover can help to reduce erosion, but it also has many benefits. So in terms, for example, improvement of soil quality and productivity. It can also reduce water and air pollution. It participates in climate mitigation and adaptation to extreme events. And it also provides many habitats for lots of species. But it also has adverse effects that we need to consider, such as increasing plant cover can lead to water shortage. And the use of single species cover can also lead to a loss of biodiversity or vulnerability to pests and diseases. And sometimes you can also observe a high mortality rate if the species that are introduced are not adapted to the environment. So this is why it's really important to choose the right type of plant cover to the given location and given context. So thank you for your attention.
Okay, thank you. Very well done, perfect timing, and nice insights. So now I will call on the floor Olivier Evrard, so to shed some more light into soil erosion. So Olivier, the floor is yours. Okay. So Olivier is a researcher at LSCE, and the background, I take it, is looking at the dynamics of soil erosion and sediments at catchment scale level with different techniques, and so please give us more insight into that.
Thank you very much. Good morning, everyone. So Nathalie asked me to talk to you about what we've been doing on the impact of some control measures to limit the problems associated with soil erosion and sediment transfer in contrast with agricultural catchments. And after seeing your presentation, I'm sure we have plenty of things to discuss about the choice of plants to limit these problems, for instance. So you've made already a very good introduction on what is soil erosion. It's not to start again with a new introduction, just to mention that we focus our research in agricultural environments, of course, because of the lack of vegetation covering and protecting the soil. These problems are exacerbated in this type of environments. But we are interested in understanding what is moving, when, where the sediment comes from, and how fast it moves through the system. So it's not really a human process because, as you know, erosion is natural, but definitely what has been happening with human activities during the last decades and centuries is that we accelerated these processes, and now they are too high to remain sustainable in many places around the world. And so it's important to put figures on how high is erosion, where is it coming from, how fast is it moving through the system, just to help giving diagnosis tools to try to control this process while maintaining activities, because you have to maintain these activities. So you've mentioned and you focused on all these on-site impacts of soil erosion in the agricultural land in particular. But once the sediment that has been produced by erosion moves from the land to the river systems, it leads to many other what we call off-site impacts, to the increase of turbidity and siltation. And when people have sediment in their cellars, they are not very happy, and this happens just like right at the moment in many places across France, and it's more and more frequent. So our specific approach and tool to focus on these processes is to try to, I mentioned it, to identify the sources, and therefore we develop what we call sediment tracing or fingerprinting techniques, which means that we identify the potential sources of sediment across the landscapes, and we analyze biophysical or biochemical processes, properties that may discriminate between these different sources, and then we compare the signature of the potential source with that of the sediment. So this is basically what is sediment fingerprinting, and it has become more and more popular in the literature because people are interested in quantifying the processes, of course, but also to understand the processes controlling them, to try to control them across the landscapes. And we have a specific tool. So I'm from LSCE, and one of our research institutions at the lab is CEA, so the French Atomic Energy Commission. And in the 60s, CEA and CNRS decided to create a lab where the idea was to use radioactivity that you can measure in the environment to better understand the processes. And so I'm quite in this part of the historical research of LSE, where we measure radioactivity to try to trace finally this sediment across landscapes. And we use, in particular, the gamma emitters, so the most energetic rays. And so you know that we live in a radioactive world for both natural and human reasons. And so we can detect natural radioactivity, but also artificial radioactivity. And one of the isotopes we detect everywhere in the world is this one, cesium-137, which is a fission product that was mainly produced during the atmospheric bomb testings in the 60s. So we know where it was produced, when, so mainly in the 60s. And he has also a very convenient half-life to investigate soil erosion processes and the impact of land use changes during the last several decades, because emitted in the 60s with a half-life of 30 years, we just cover pretty well the period since with the agricultural intensification across Europe, for instance, and now in other regions of the world. And cesium, so it's emitted during this type of bomb tests, and then with rainfall, it will just be brought back to the soil, and once it is in contact with the soil, it will bind very strongly to the clays and the particles, and then once it sticks to the clay, it will remain with the clay. So if the clay or if the sediment gets transported and moves across the landscape, cesium will remain attached to it. So it's a good tool because of its affinity for the fine particles to trace the particles across the landscape. On this graph, you see just an idea of the proportion of the cesium fallout around the world for the different latitude bands, so in the northern hemisphere and then in the southern hemisphere. And actually, we find 75% more or less of the fallout in the northern hemisphere, and only a quarter of what has been emitted in the southern hemisphere. And this is just related to the location of the bomb testing sites. And most of the tests took place in the northern hemisphere. So now, so here in Paris, like we are in the best latitudinal band somehow, where we have the most season fallout to trace particles, if we see the things with that vision. So today, because when I've seen your report about the Grain for Green project, I chose to show you two case studies in Asia, but not in China. The first one is in Laos, in the tributary of the Mekong River. And then the second one is in Japan, in Fukushima, because you can make the link with the season. There has been a recent season fallout and a lot of land use change questions in this region. So I thought these were appropriate case studies to discuss the link with land cover and soil erosion in Asia, although it's not in China. So if we travel to this tropical catchment of Laos, so you see pictures with evident signs of soil erosion. So it's work we've been doing with colleagues from Laos and from IRD. So actually, they installed, you see, so this is we are in the northern part of Laos, nearby the city of Luang Prabang. Luang Prabang is here, so it's along the Mekong River, and they were interested in the system draining into the Mekong River, including the Houay River, and then another small tributary here, which is called Houay Pano. So actually, they equipped this catchment, so it's a small catchment, about 10 square kilometers, but this is representative of the areas we find in the region. And it was equipped for river and rainfall monitoring since the late 90s. And this is affected by the monsoon, so with these very steep slopes and heavy rainfall, you can imagine that it's a critical place in terms of erosion. So they installed the monitoring stations in the 90s, but of course, after that, they don't control what happens in terms of land use. They just follow what happens, but people are, of course, free to choose what they cultivate, for instance, in their fields. And what happened? So it started to happen after they started the monitoring. Is that what they call the teak boom in this part of Laos. So basically, it was initially an incentive from the authorities to start to diversify the production, including the production of teak, which is used just like for your furniture in the garden. And many things explain why it was very successful, because there was a demand for that at that time. They changed, so Laos is a communist country, but they started to give incentives for people to start their own activities. They constructed roads, and so on and so on. So there was a whole context to push people to start planting teaks. The problem is that if you look at what a teak plantation or a hill slope covered with teak looks like, it's this type of picture. So you have these very high trees, and the problem is that for the local people, if you keep vegetation under the trees, your plantation is not clean, so what they do is that they burn the understory vegetation. But you can imagine that in these erosive conditions, if there is heavy rainfall or the monsoon starting on these tea plantations without any understory vegetation, you see immediately that there is a huge erosion problem. You see even the roots appearing here. So in the past, what they did, it was a slash and burn system. So they had very long crop rotations on these steep slopes with different foods, mainly food crops. And people started with these incentives from the government to stop cultivating these very steep slopes and just wait for the teak to grow. And then when it's ready to be sold, they cut it and they sell it in the market, which is definitely maybe easier than cultivate very steep slopes. But you see that within a few years, you trigger a huge erosion problem in this quite fragile area. So in terms of land use change in this very uppermost tributary of the Mekong River, so you see different colors, but basically what we are looking at now is the dark blue color, which corresponds to the surface occupied by teak plantations. So you see that in 1998 you have, so here at the outlet you have a small village, and nearby the village you find the initial teak plantation. Then in 2006, you see that there are more patches with teak plantations across the landscape, and in 2014, you see that now teak plantations are occupying the majority of the catchments. So within a few years, or a bit more than a decade, you have a very strong land use change. So I mentioned about this problem of burning, which is very common in the whole region, not only in this monitored area. Yeah, you see the problem after burning and after rainfall occurring, that you have a lot of erosion. The problem is that you see it, but it's different to observe something and you introduce this in your presentation. Then how can you quantify this, just to compare things in absolute terms? So you have the main river, which is here in the valley, which is permanent. And the colleagues from RRD, they installed this type of monitoring stations on the main river, of course, but also on different hill slopes where you have ephemeral slope. So only during the monsoon, basically. During the rest of the year, it remains dry. And so they didn't control the land use change, but we were fortunate that at that time they equipped hill slopes covered with a teak plantation, and on the other side of the valley, hill slopes covered with annual crops, so that we could compare the signal from the two different land use situations. And typically in 2014, there was a very heavy rainfall event, and you see that both in terms of runoff and sediment production, if you compare the hill slope covered with a teak plantation, which is this curve, versus the one covered with annual crops, whether you look at runoff or erosion, you have a dramatic difference between both situations, with a much higher production of both runoff and sediment, and the village at the outlet was flooded, which was the first time. So definitely, if you increase the teak plantations across the landscape, you increase the problem at the outlet with these muddy waters entering the houses. And so the good point with this monitoring system is that you can look back from the early 2000s until 2014 in this case. Of course, you have rainfall variability during this period with the drier and wetter years, but basically after 2009, where you have a significant proportion of teak plantations in the catchment. So this is the brown part of these hexagrams. What we observe very clearly is that we have a decrease of infiltration and an increase in runoff, despite the rainfall variations, and also a very large increase of the sediment load, both as wash load or bed load. So we could also make a statistical test and check that this difference between the period before 2009 and after 2009, these changes were statistically significant. So within a few years, although you are planting trees, you dramatically increase soil erosion in these very steep hill slope environments, which was a bit counterintuitive, but because This difference is due to the management of these plantations and the plant cover. So basically, we could now estimate the sediment yield change before and after the increase of the teak plantation. So it was about 100 tons per square kilometer before at 2008 and more than 600 after. So it's really a dramatic impact and a very strong increase in the proportion of overland flow recorded at the catchment outlet. So of course we participated to this project, and we also analyzed cesium 137 because it's our favorite tracer. And what you can do with cesium as well is to discriminate the surface layer of the soil, which receives the atmospheric fallout and which is stacked with cesium, versus what will be produced in landslide area or channel line collapse areas, for instance. So subsoil that has not been exposed to the fallout and which will be depleted in cesium. And interestingly, what we observed, so here you have the cesium concentrations in bypass per kilograms. And what we observed is that, so we have different type of samples here. What we observed is that this is typically what you would observe in this surface layer of the soil, like 2 bypass per kilogram. This is what we would observe in landslide material, which means no cesium. And interestingly, what we observe is that if you collect soil under teak plantations with increasing ages, but you can even quantify the decrease in cesium concentration in the soil below the teaks, just because erosion is so massive that all the soil is being eroded and transferred downstream. And we could do the same with the sediment collected at the monitoring station. So we have somehow a change of behavior, a change of processes, and a change of sources signature just because of the magnitude of erosion in this system. So we come to the potential recommendations to avoid this problem. Of course, you could say, please don't burn the understory vegetation, but maybe it's not enough to convince them not to do it. So what our colleagues were trying to do now was to convince them to implement agroforestry practices, to plant species that will not compete with the teaks, of course, and that will provide extra money for them. They will have also an economic incentive while protecting the soil against erosion. So typically you see that this looks very different from the previous pictures. So this should be the way to go to keep it protected while interesting on the financial point of view for the local farmers and the local population. So now we travel across Asia in the east direction to Japan, where we've been involved since 2011 with the French and Japanese colleagues in the post-accidental Fukushima monitoring, and you'll see at the end that there will be in the end a question about plant cover and the link between plant cover and erosion. So typically the idea initially was this one. So we knew, and we've seen on TV actually live these explosions, nuclear explosions, a few days after the earthquake and the tsunami affected the eastern coast of Japan. Explosions emitting regional including cesium 137 in the environment. And then on the 15th of March 2011, there was rainfall and snowfall in the main wind direction coming from the Overland. And this led to the fallout and the deposition of cesium on these landscapes. So we are in just like almost all Japan looks like, it's a very mountainous area, which is also affected by heavy rainfall events, mainly during typhoons in summer. So the idea was, okay, we are in mountainous conditions with erosive conditions as well. So probably the initial fallout of cesium and other orogenic will move across the landscape because of erosion. So the idea was to monitor the dispersion of the initial radioactive fallout across these landscapes. So if we look at so we are in northeastern Japan. This is the Fukushima Daiichi nuclear power plant, and all the dots you see on the map are permanent rainfall monitoring stations from the Japanese Meteorological Agency, and we just collected all the data to quantify the rainfall variations throughout time and also across space. So basically, you have drier winters in Japan and very humid summers. So this is the total precipitation, but if you look at erosivity, you have an even more pronounced situation with the major part of erosivity taking place, let's say, between July and October, and most of it will take place during typhoons. So when there are typhoons coming from the Pacific Ocean, depending on the area, they will flow over in Japan. They will lead to potentially very high erosivity rainfall. The other map is what you see in the background with the colors corresponds to the cesium deposition on the soils of northeastern Japan. So in red you have the more contaminated area, in blue, less contaminated areas. So you have this plume like extending to the northwest of the power plant. Like this is where Fukushima City is located, like 70 kilometers away from the power plant. And what happens in this region is that you have a network of coastal rivers we see here that drain the main cesium plume on land and drain it into the Pacific Ocean here. So we have a series of different coastal rivers here draining the main part of the contamination plume. And then we have another system here draining, which is the Abebssi river system, draining a less contaminated but a more expansive area of the plume. So initially we were also very optimistic, and with the Japanese colleagues we installed like beautiful river monitoring stations. But even in 2011, after the accident, when the project started, there was a big typhoon, and this typhoon flushed away all the river monitoring stations. So what we did as a surrogate method for monitoring is just collect flood deposits, lag deposits, which are very easy to find. Just because the system is so erosive, you can select and sample the recent deposits of fine material in the channel. So we did this as surrogates during the first campaigns, and then after we continued because it was very easy and convenient to monitor many points because we covered all these wet points, covering a significant part of the main radioactive plume. If you look at the activities, again, like in Laos, it's in becquerel per kilograms. It's said that we are not at the same level of concentration. So in Laos, we had 2 becquerels per kilogram. You see here that we start at like, this is 10,000, 50,000, so it's much higher. But what you see, if you look at the evolution after the main typhoons and the snow melt, so 2 campaigns per year, is that we have variability because the plume is heterogeneous and you have also differences depending on the local conditions. But basically, you have variations, and after 2015, we see a very strong decrease in the cesium activities concentrations, continuing like in 2016, 2017. We are not back at the cesium background level due to the bomb fallout. We are much higher, but still we decrease this by about 80% at this stage, which probably reflects a change of source, and also the fact that Japanese authorities decided to implement a decontamination program in the agricultural areas of Fukushima. And so this probably explains why the cesium levels in the river sediment decreased so strong and so quickly after the accident. So these are probably this decrease in cesium concentration in sediment is explained by the 3 potential explanations: exports during typhoons, with heavy rainfall leading to floods and flushing the material towards the Pacific Ocean. The decontamination program as well, because the idea was to remove the topsoil layer concentrating the cesium-137 in agricultural and residential lands, and to store it in, so they remove it and then they store it in big bags that you could see everywhere across the landscape. A third reason is also when you have what I introduced in the example from Laos, if you have these mountainous conditions with very heavy rainfall and that you have a channel bank collapse like on this picture or landslide, you will produce a lot of material that has not been exposed to the initial atmospheric fallout. And so this material that comes from subsoil layers will dilute somehow the signal borne by the surface layers. So what we did is to investigate in particular the impact of this decontamination, because it was the first time in history, and we hope it will remain the last time as well, that decontamination was implemented after nuclear accidents. Because during the previous major nuclear accident in Chernobyl, actually it was decided to evacuate the people and then just make the area protected area without inviting the people to return and without implementing decontamination. They just keep the contaminated area intact, they don't touch it anymore. In Fukushima, the Japanese authorities chose a different option, which was to reconquest the area, decontaminate, and invite people to return. So this is just a sketch explaining that for decontamination at agricultural lands, you remove the topsoil, concentrating the cesium, and cesium is really concentrated in the topsoil layer because it binds to the clay, so you can't go deeper. But then what they did is that we don't really understand why, but they didn't want to remove soil without putting a new soil instead. So what they did is that they opened quarries, and the background there you find granite, and they just opened the quarries, extract it, and crush the granite and put it instead of this topsoil layer. So you see that you can imagine that as an agronomist, you can imagine that putting crushed granite on fertile soil is maybe not the best agricultural decision. But definitely this was done. So they conducted this decontamination program in agricultural and residential areas only, across a surface of about 9,000 square kilometers, which is probably very small compared to the Green for Green project area, but still significant. It's like about the area of Ile-de-France region, or Corsica, to give you an idea. And they only targeted the residential and agricultural areas, so about 10 to 15% of the total surface. The rest is forest, and they didn't touch the forest. The forest is still intact. Doing that, they produced 20 million of cubic meters of this material stored. And this costed like 24 billion euros just to remove them. And the problem is that they started to reopen the area and invite people to return, but by last year, very few people, like 10–15% of the initial population returned. So this raises a lot of questions about not only the, let's say, the physical effectiveness of the contamination, but also about the cost effectiveness of the whole process and the added value for the local population. So because doing that with this amount of money and producing that amount of waste, they didn't touch the forest. In fact, they just decontaminate around the houses, within a radius of 20 meters around the houses, and the rest they don't touch it. And also in the region, you find a lot of reservoirs, which are used like for irrigation for paddy fields. But of course, these are excellent tracks of sediments. So sediment in these dam reservoirs. What happens to regenerates in forests? So this is a very complicated cycling process, because you can imagine that during the accident, when you have the fallout, it will depend on whether it happens on a broadleaf forest or an evergreen forest. And in Japan, in this region of Japan, you have both types of forests. Because the accident took place in March, so in March it's early spring. So broadleaf forests, you don't have any foliage, whereas, of course, in evergreen forests, you have the trees with the mediums. So you have a different cycle and a different timing of the distribution from the canopy to the soil, but what our colleagues working on the first sites showed in a recent review is that they show, even after 6 years after the accident, the proportion of the season fallout that took place in the forests, whether it's an evergreen forest or broadleaf forest, now it has been transferred to the soil layer. But still, you have part of it being transferred by the roots to the trees, which cause a problem for the exploitation of forests and wood, for instance. So we've been interested in what happens in these dam reservoirs, and if you collect the sediment core, you can find the peak of cesium related to the accident, and then investigate what happens in the landscape in terms of erosion. And then now the main questions remaining are related to what I showed you when I introduced how the decontamination was made, is that there are a lot of questions from the farmers and local populations about, of course, soil fertility after putting this crushed granite on land. The potential, although most of the cesium was removed when they removed the topsoil layer, there's a bit of cesium remaining, and people are a bit worried about the potential transfer of cesium to the plants. So the decision on what plant to cultivate is important. Questions about fertilization, for instance, putting potassium enriched substances on land, which is interesting in terms of cesium transfer control, because potassium is analogous to cesium. So if you enrich the soil in potassium, there will be less transfer of cesium from the soil to the plant. But farmers don't like it so much because for them it's a cost with no benefit in terms of production. And then we have, this happened after a very strong typhoon in 2019. It was a big erosion event in forest that has not been decontaminated. So it's also a question about the perennial supply of contamination sediment from the forest, now that the land, cultivated land has been decontaminated. To make it simple, political decisions change all the time in Japan as well. And so since 2011, we have had changes of government and decisions. So you see again, the background map is the cesium fallout map. So this is the situation of the restricted access areas in 2011, and this is the map in 2017, when they started to reopen the decontaminated areas. So initially, all this area was closed, and it matched the high contamination area. Then in 2017, they started to reopen, for instance, this village and the borders here and there. And you see here a red line in the most contaminated area. It was, and it's still restricted access area. And the idea was to ban people from this area for like 30 years. But now the latest Japanese government decided that it was not possible to ban people from returning to this area, and so they will reopen it from this year, without any decontamination program. So they started to decontaminate here and there on the borders, and in this area as well. But here, which is initially the most contaminated area, that has not been decontaminated in the past, will not be, and will be reopened anyway. So this raises a lot of questions about just, of course, it's a lot of problems and questions for the local populations, you can imagine, but also in terms of cost effectiveness of the management of this type of situation, it raises a lot of questions. And we have colleagues from another division of CA interested in biotechnologies. They are thinking about a new way to start with new agricultural activities in this land. So the discussion now is that there are so many discussions, and also people are so worried about food products produced even after decontamination, even if you show that it has been effective. People are not very positive about the fact that they could grow food crops again. So the idea here was to propose safe use crops, which means crops that you use for producing bioenergy or for producing biomaterials, like industrial textile materials, type of things. So they propose like the use of flax, hemp, or a certain type of miscanthus. Yeah, the question is, if you start again with these crops in either decontaminated areas or areas that will never be decontaminated, what do you observe in terms of fertility, production, soil erosion, cesium output? It remains even almost 10 years after the accidents. A site where you have to experiment and continue monitoring to investigate what happens if you take this decision instead of that other one decision. So as a conclusion, you showed it, and we've seen other examples that soil reservoirs are increasingly threatened by erosion, among other threats. That sometimes there are very ambitious mitigation programs and very costly, but it may be effective for some applications and not for others. And so what happens typically in Fukushima, I think, is a good example. Sometimes you take a decision with that objective, but then there are feedbacks in the system occurring that you didn't think of or you didn't expect to be so strong. And they may even threaten your initial strategy. So typically, I think that this type, and we introduced it with your projects, of integrated approaches are needed to avoid the situation. But it's difficult as well to tick all the boxes, like to have catchment-based approaches, interdisciplinary solution, participative approaches, because if local people are reluctant to adopt your solution, nothing will happen. So I think I'm getting to the end. Yeah, just to thank you for your attention.
Thank you, Olivier. Very interesting perspective. I think there are many connections with the other talks. So I will call again the group to the floor, and we'll start the Q&A questions and answers session with.
So you have to sit on the table.
I think
you can stay up.
there will be this can be sort of round tables. Sit on the table, and then and go on the other side. Basically, yeah. So it can be a little bit of an exchange between the two sets of speakers, and then we'll open up to the two rooms. So, any points you'd like to share?
I have an idea.
Yeah, you can go ahead.
You can go ahead. Yeah, my question would be, so you showed this very ambitious program in China, but did you have information about the cost of this project? And
yes, we already mentioned that. It's more than 4 billion euros. It's about 43 billion euros, something like that.
Which in case, because it covers the whole of China?
Not the whole, but almost all the area. It's like it covered 25 provinces, more than 90% of the area. But it's not like 100%.
And then 43 billion euros.
Yeah.
So if you compare this to the Fukushima figure on 9,000 square kilometers, 24 billion euros. And do you think that, so I think it's nice to compare the figures just to see, you have the impression sometimes it's a big priority, but if you compare the figures with what has been really done, maybe it's not as big as solved. And the other point is that among these, I don't know if among these 43 billion euros invested in China, there was part of it devoted to the monitoring, because it's good to invest money in proposing solutions, but sometimes when you spend so much money to implement solution, it's maybe good to spend part of the money to monitor that it's really effective, or maybe it has unexpected side effects. I don't know what's your position on that.
There was some research stations that were built, and that it was mainly coming from the research, because they wanted to see like the evolution from the first provinces where it was implemented, and to take into account the positive results, but also the negative results, to consider this for the future implementation in the other provinces, because it was really dynamic. It was only done for a few provinces, and then it really spread. So they wanted to have information on what was things that they could improve, but it was mainly from the research.
Yeah, and for the investment also, it was not like dedicated since the beginning of the project, because during the first year, it was managed only by the local government, which is concerned only 5 or 4 provinces. But after we have the contribution of the state, of the big government, and at that time it covered more space and more investment also.
And maybe it hasn't been so expensive also because it was a nature-based solution. So the way was to give just subsidies to farmers in order to make them participate to the project, so it can justify why the speed it was in a green part of the China, it wasn't so expensive than the Japanese project.
Can I just follow up on that? It's a really important point. I think yesterday our speaker said from IUCN that projects have to be self-sufficient. They shouldn't need subsidies, and so that's maybe a long way to go. But it's in terms of sustainability and stewardship by local populations in the long term, that's really really important. And it's probably one of the lessons, I guess, from this Green for Green project, that if you don't create added value, that's what the point made by Keynote also yesterday. It's not sustainable in the long run, but it's a challenge.
I have a question concerning your presentation. If I'm not mistaken, you said at the beginning that at LSCE we use radioactivity to know where the erosion starts and in which speed the particles are transported. So I wanted to know if taken into account the uncertainties due to the radioactivity, why did you choose this way? Because I think it should be dangerous for maybe animals, plants, and humans, when we know that surface water is sometimes used to produce a drink water after, and we don't know exactly what happened with radioactivity after 5 years. Sometimes it increases, etc. So why did you choose this way despite the...
An important point is that we don't introduce anything in the environment. It's a tracer which is already present in the environment. So sometimes it's anthropogenic, like sediment 107, but I didn't emit the atmospheric bombs. But it's a good point because there are also natural isotopes, and I didn't explain it here because it was not the purpose. But we also have different radioactive isotopes falling on the ground with rainfall all the time, continuously, but they are natural. And the good point is that they have different half-lives compared to the cesium-137, and as they are produced continuously, if you combine the different isotopes, we can really we can use them as chronometers and constrain the time transfers of polymers.
Yes, Sebastian?
Yeah. Well, you mentioned a lot of wet deposition about the isotope and so on. Is there any dry deposition?
Yes.
Or with erosions that is implied?
There is dry deposition. What we measure actually is the total deposition, but we know that the wet deposition rate is dominant.
The most okay.
Mm-hmm.
Thank you.
Yes, please.
I do have another question for you. It's about one of the last slides you showed with the red line. And you say that around it was contaminated or almost, but how can you, how are you certain that the contamination will not spread out? I don't know how it works exactly, but is there a possibility for the particles to spread and to contaminate around? And how can you, do you have to reevaluate the area? Or, because we thought about erosion, so I suppose it plays a role in
Yeah, there was definitely our point when we started this project. That's what was our fear, is that they would be transferred. But still, this transfer will be mainly constrained in the river network. But definitely, you have transfer potentially from these areas to these areas. You see they are in blue, but they drain with catchment areas in the yellow or red area. So there is transfer in the floodplain. But still, it's except if you have big flooding and overland transport, it remains constrained in the river channels. But this was definitely one of our main points. The other point, and maybe it brings me to your part of your question as well, is that typically the cesium-137, as it really binds strongly and almost irreversibly to the particles, you don't find it in the water anymore. In the immediate post-accidental phase, you had cesium part of it in the water, but after, it will only move with sediments. So typically, you don't have problem in the groundwater. You have problem with other isotopes, but not with cesium-137, because it will remain stuck with the ground above it. And but this is typically a political decision. And you're also aware that there are lots of discussions about the Olympics that were scheduled last year, and we don't know if they will take place this year or not. But also there was the Japanese government wanted to show that the situation was normalized. So I think this also plays a role in the fact that they really want to reconquest this area.
Okay, we have a question on the chat on the, I think this is more for the first group, but I guess also for the mitigation options, but pond cover and providing production, is it a criterion to select the plants? You mentioned suitability to the soil and the climate conditions, so
yeah, exactly, I agree with that, but for each project, for each kind of plant cover, it depends on the objectives of the project. Like if it's we are going to make a plant cover just to protect the earth. In this case, we are not going to talk about food or fodder. But in the GCP, some of the main objectives of it was to face the rural poverty. Then food and fodder is one of the criteria that should be taken into account. Maybe here we are talking about agroforestry or using trees with fruit, or to have like wood or timber to get more revenue for the farmers or the rural population.
Okay. Was this also a criterion in your case? You mentioned different species for the understory layer or vegetation.
Yeah, they wanted to.
That they were actually also used for. Yeah.
I have a question. Going back to the example of Laos. So agroforestry, was that really implemented and widely used, or it just stayed in small areas? But if so, I mean, the big gap between implementing was just a knowledge that people didn't know that they could do it, or was also.
Yeah, typically I think no, it was not widespread at all. It was really a niche, you can say. And the question is that there's really this very strong belief, and somehow you find this strong belief like in the French countryside as well. For instance, some farmers at least, they will say that they put glyphosate to just clean all the weeds, well, clean the weeds, remove the weeds, and if you have weeds on your fields, you don't maintain it well. And it's really the same situation in Laos, where if you have growth of plants underneath the trees, people say that you don't manage your field well, it's not clean. And maybe it's just a matter of discussing and, I don't know, raising consciousness about the fact that it's maybe more complicated than that. And so that the idea of agroforestry was also to show them that they could have an extra income, the production, with more productions. But on the other hand, depending on the understory that you plant, you will probably have more work than just waiting for the tree to grow and grow the onions vegetation. So I think it's part of the discussion.
Sébastien?
Is there any strategy in terms of plant cover as bioremediation or radioactive?
Yeah. So this was a big discussion with the colleagues. So initially, the idea is to make yes, what they call phytoremediation. But the problem is that you can find plants that will absorb preferentially cesium, but the problem is that the quantity of cesium you will remove from the soil doing that is not sufficient, and you need so many crop cycles to remove cesium from the soil. It's absolutely not cost effective. And also the problem is that you have a lot of contaminated biomass, and you come back, okay, you can burn it and reduce the volume of it, but still you have contaminated biomass. So now what they try to do is just the opposite. Instead of planting vegetation that pumps the cesium preferentially, they will plant vegetation that doesn't pump the cesium at all, and maybe select those plants that even less than others will pump cesium from the soil. But then still, for me, there is no, it's completely new, this decision that they will never say never, but that they will never decontaminate this area, and they give incentive to start a new agricultural production there. You can say, okay, I will implement safe use, so no non-food crops that don't pump the cesium at all, but still it means that the soil remains contaminated and will irradiate the farmer going there. So although you will probably not stay there for long, I'm not sure that's the best solution. So there was maybe also a question I had for you, because maybe you can have ideas or critiques about the choices made in Laos or in Fukushima. Did they choose or did they promote the good plants? And then the second question would be, okay, the good plants for what? Because it's difficult to tick all the boxes. Like, now we should we should eat local food, which is organic, sustainable, and then somehow, okay, you can eat an organic apple from South Africa, which is maybe good for farming in South Africa, but on the other hand, it's not good for greenhouse gas emissions. It's difficult. I mean, it's difficult to tick all the boxes. So maybe somehow you have to make a compromise or give the priority to some criteria, depending on the local situation. I don't know what's your opinion on that, and maybe you have thoughts about what has been promoted in Fukushima or in Laos. Is it good? Not good? Maybe there are other ways to go.
For the teak trees, so I think it was mainly done for economic reasons, but so maybe that's why it's not a systematic evaluation, and maybe we could have results in terms of economy, but also, for example, the cover grass, it could also have been promoted, and we could have maybe better results. More systematic evaluation. It could have been planted with some teak trees, but could have been combined with other measures to improve the results.
And to add, I want to say that as it's difficult or maybe impossible to do everything perfectly, it's why we propose in our project is to build a, for example, a matrix with some coefficients. To build, for example, a matrix with some coefficient according to the different goals of the project, and to try to do some combination and see which one give the better result before choosing.
Okay. Just to add the information about how to take into account all the requirements, I think it's a little bit difficult and it's a complicated system or equation, but at least we have to consider the main requirements. For example, for the GGP, we got a very high rate of mortality of plants, like to avoid like this rate of mortality. At least we have to keep the plant like alive, and before thinking about other objectives or goals.
Okay, questions on the...
So you all agree? No?
Yeah.
So you all agree that you have to give priority to some criteria, and you cannot tick all the boxes.
Yeah, I think that the main objective is to make successful plantation before the other objective. Like we are here to plant and to defend the life of the plant as the first like requirement, and after it comes like the other necessities or the other objectives.
Yes, to make criteria according to me its environment, because we should first do a project that will not destroy too much the environment, and after we can consider other criteria like social and economic ones.
Okay. Anushka,
Yeah, somewhere in the presentation, somebody mentioned that the natural vegetation does not really prevent soil erosion. So I didn't understand how it's possible or is it actually completely true. So, somebody knows the process and how does it work on. Is it I said somebody mentioned that natural vegetation is not really preventing soil erosion, does not really help in soil erosion. So, because yesterday we presented that naturally regenerated forest would be better, and for biodiversity. So I was thinking if that's relevant in terms of you mentioned in the site conditions. I think that natural species versus there was something. And
maybe it was just to mention that some studies decided to use non-native species because they wanted to obtain maybe faster results in terms of erosion, but it doesn't mean that you will not have other consequences on the environment. And for the rainfall project, there are some other studies, like for example, they monitored the restoration, the natural restoration of vegetation, and then find that it was better for erosion than the studies that use non-native species. So we can think that for erosion, it might be better to have a native vegetation that is restored.
yeah, I mean, I didn't want to ask you, I was just generally asking you because we are having two presentations.
Okay, for me, I think that the natural plants, we don't have a problem with the natural plants for the ecosystem or for the erosion, but the problem comes with the human, with the intervention with the anthropogenic actor. If like we don't intervene to modify the ecosystem, it will be like goes okay without any problems. But we are here just to correct what we did like, as a human. That's why we intervene for that kind of project.
Okay, yeah, I think both are applicable. Okay, next discussion. Sebastian?
Yeah, you mentioned that we should foster natural plants, but most of them are green. So how do you deal with that? And then how you make sure that are going to be relevant plants for food or whatever, or energy, as you mentioned?
Yeah, that's why we try to give some essential criteria for choosing the kind or the type of plant, because here, as I said, the first like objective is to reduce soil erosion. Like we have to plant plants with a huge like root system to fix the soil as the first step. And after we can think about the food or to defend like poverty, local poverty or other requirements. But for the GGP, we didn't arrive to get like a successful plantation because we had like a very high rate of mortality. That's the point that we were discussing as well.
Okay, any other questions, issues, or in the virtual room? I would have then one question that is the scale actually, because you emphasized in the first talk, you emphasized so selection of species, and we sense a sort of field scale, local scale, and then Olivier also emphasized the catchment scale, because obviously there are many things happening after the soil, the sediments have left a given plot in the landscape. So would you take that point on board in your project, that you should think local, but also at this catchment scale, given the hydrology of the system and all the dynamics that Olivier explained?
Yes, I think we have to take into account the site characteristics or implement yes, because we have to take into account the site characteristics, but it's not the only factor that we have an influence on our vegetation. So yes, ecology depends on where it's located. If there are some other vegetation above, for example. So yes, I think it's we have to consider our plots, but also like the surrounding.
Okay, and then what kind of approach, maybe Olivier, you could help at that point, but what kind of approach could you use for that landscape scale, watershed scale design?
And we think that thanks to remote sensing again, it's possible to have an overview of the site and the around one, and it's generally a very interesting tool that can help for that.
I had an idea when I read your report, and because we tried to discriminate the source. Okay, we use a lot of geochemistry or physical, chemical properties, but there's also the biological properties part. And we have colleagues in the Alps who started to use the environmental DNA. And so we were interested in the sub-community looking at the sediment DNA. So when the idea is, okay, when the plant dies, you will have this DNA signal bound to the clays like sediment does somehow, and it works quite well. And it depends on what you are looking for. But so what we figured out, for instance, when we tested it in Fukushima, because we thought it was perfect to check whether we have different vegetation signatures in different rivers. For instance, one river draining forest only, and another river draining like cropland only. And we were very surprised by the results that we found, like in the cropland river sediments, because we had a lot of vegetable signatures and so on. And actually we found, looking at the agricultural sensors before the accident, that in this area they grew vegetables, not only rice. But so you see the vegetations that tagged the soil before it got eroded, and you have the answer at the outlet. Where does it come from? I mean, from the landscape, you can target the plants that tag the soil. So maybe this could be a nice approach to conducting the Chinese projects.
Yeah, in terms of tracking where the particles come from in the erosion. Yes.
Or even to know what there is in the soil,
right.
Or you mentioned samples.
Okay, very nice. Any other questions? We're nearing the end of a long morning, so I think we'll close the session here. Thank all the speakers.